Hello everyone, welcome back. So today we're going to be talking about the planar kinetic equations of motion, and specifically we'll be focusing on translation. There we go. Pen's working this time. So you're going to learn about the three equations of motion for a rigid body in planar motion. Like we've done these equations before, but now for a rigid body. You're going to analyze problems involving translational motion. So let's jump right into it. First off, why do you care? That's the big point we always should start with. Well, for one, if you look at this boat and trailer, they undergo rectilinear motion. So tractor moves forward, trailer moves forward, boat moves forward in a nice straight line. If we wanted to find the reaction of the trailer's wheels, as well as the acceleration of the boat, we'll need to draw a free body diagram and a kinetic diagram to see which direction is it going and what forces are helping it to go in that direction. So how many equations of motions would we need to solve this problem? And what would they be? Now, hopefully you're remembering your statics and some of the forces in the x, some of the forces in the y, and some of the moments. And we'll get into that a lot later. Okay, now how about this one? Well, as the tractor raises the load, the crate will undergo curvilinear translation. If the forks don't rotate, they stay nice and flat the entire time. The angle doesn't change. And so it's moving in this curvilinear path. Well, this is different. So one thing that you probably can already do in your head is you can answer this question. If that load is raised too quickly, will the crate slide to the left or the right? And the answer is, it's going to slide that way, okay? I think pretty much anybody could guess that because you've seen things slide off of things and you know how reality works. Your brain is this amazing physics engine and it's doing that for you. So another question might be, well, how fast can we raise that load before the crate will slide? What's the answer? Well, we're going to have to solve our equations to figure it out. And so what are those equations? Well, we're going to have to look at planar kinetics, and in this case, we're going to say planar kinetics of rigid bodies that are symmetric with respect to a fixed reference plane. So when a body is subjected to general plane motion, it has a translation and rotation. And to start off, we're going to break those up into translational and rotational motion and look at them separately. So what is our coordinate system going to be because this thing is moving and spinning? Now, what we normally do is we're going to pick an arbitrary point P within our body. That can be the center of gravity if you want it to. It does not have to, but it's just an arbitrary point. We're going to say that our coordinate system is fixed to that. Now, while your coordinate system can move with the body if you want it to, it should not rotate, okay? It does not rotate if your body is rotating. Now, if the body undergoes translational motion, then the equations of motion is simply our force equals mass times acceleration. In this case, though, we're saying acceleration of the center of gravity because that's just taking into account all of that mass and putting it at a single spot. If you want to, you can write that in these scalar forms right here. So all those external forces acting on the body is going to be equal to the total mass of the body times acceleration of its mass center. Now what about rotational motion? This is a little bit more difficult because we've worked with this a bit in the past. We're going to have to use some different terminology now because we have this rigid body. So first off, we know that the moment about this arbitrary point P can be written as follows. Like, you have all these forces, and all those forces are some distance from P. And so the moment is simply going to be equal to R cross F. And maybe you also have applied moments on this surface. Well, it's going to be equal to your moments right there. And so if we multiply all that out, what we get is that's going to be equal to this right here, crossed with our moment times the center of gravity. Sorry, not moment, our mass times acceleration of the center of gravity, plus moment of inertia around our center of gravity times alpha. If you're wondering what this is, it is simply our distance to our center of gravity. Now, this term right here, where we have the sum of the moments acting on it, is called the kinetic moment about point P. The kinetic moment about point P. So one last thing to do right here. Now, if that point P that we work at coincides with our mass center G, then it makes it really, really simple. And we have a simple equation where it says the sum of moments around our center of gravity is going to be equal to the mass moment of inertia times the angular accelerations, which is very, very similar to our sum of the forces is equal to mass times acceleration. So what this gives us is 3 independent equations, our scalar equations for a rigid body undergoing rotational motion. We have our sum of the forces in the x going to be equal to mass times acceleration of our center of gravity for both the x and y directions. And then finally, one that's taking into account rotation with the angular acceleration and the mass moment of inertia being connected to the sum of the moments around a particular point. And yep, that's it for this time. So next time we're going to jump into translation again and develop that a bit more for rectilinear and curvilinear motion. Thank you for listening, and I'll see you all next time. Bye-bye.